A long-standing Uranian mystery gets an update. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. For decades, Uranus has baffled scientists. Voyager 2's 1986 flyby suggested that the ice giant wasn't radiating any extra heat, but new research has finally cracked the case. I'll talk with Michael Roman, assistant professor at the Universidad Adolfo Ibáñez in Chile, and co-author on a new paper showing that Uranus really is giving off more heat than it receives from the sun. We'll also celebrate the discovery of a brand new moon around Uranus in this week's What's Up with our chief scientist, Bruce Betts. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Uranus has a reputation, partly for its name that's the butt of endless jokes, but mostly because it's just plain weird. This ice giant spins on its side, tilted nearly 98 degrees. That tilt gives it some of the most extreme seasons in the solar system, with decades of daylight at one pole while the other one is locked in darkness. Its atmosphere is strangely bland compared to Neptune's stormy skies, and yet it hides mysteries that we still don't fully understand. One of the strangest puzzles was uncovered by Voyager 2 in 1986. Unlike Jupiter, Saturn, and Neptune, which all radiate more heat than they receive from the sun, Uranus appeared to be in perfect balance, giving off no excess heat at all. We would say that this world seemed to be in thermal equilibrium. That made it a definite oddball among the giant planets, raising big questions about its history and interior. We expect our giant planets to radiate more energy than they receive from the sun because they're still slowly cooling off from their formation, leaking leftover heat from their interiors into space. Now, new research has finally rewritten this story. The paper called Internal Heat Flux and Energy Imbalance of Uranus, which was published in the Geophysical Research Letters on July 14, 2025, by lead authors Xinyue Wang and Liming Li, confirms that Uranus is indeed radiating more heat than it receives from the sun. It's still less than the other giant planets, but definitely more in line with what we would expect from this world. Their work is also reinforced by other recent studies, including by a team led by Patrick Irwin at the University of Oxford. Joining me now to explain what this means for Uranus, for ice giants in general, and even for our understanding of exoplanets, is Dr. Michael Roman, assistant professor of physics and astronomy at the Universidad Adolfo Ibáñez in Santiago, Chile. He's one of the co-authors on this study and an expert on planetary atmospheres, especially when it comes to ice giants like Uranus and Neptune. Hey, Michael, thanks for joining me.
Hi, yeah, it's a pleasure to be here.
Or should I say, bienvenido? You're coming to us from Chile, right?
Yes, from Santiago. I started this recently here at the university on the eastern side of the city, Universidad Adolfo Ibáñez, where I'm an assistant professor.
So you spent most of your career studying the atmospheres of Uranus and Neptune. What first drew you to these ice giants?
I suppose Uranus and Neptune, they kind of occupy a space where they're at the very edge of our solar system as far as the giant planets are concerned. And they are far less studied than Jupiter and Saturn. So there's a lot of mysteries that remain about them. They're sort of enigmatic in that case. But they're close enough where we can actually see them through telescopes and resolve, clouds on their atmospheres. So, yeah, I think they're just sort of mysterious outer worlds that we've had some idea about, my entire life. And I remember, first seeing those Voyager images as a child. And we're at a position, I suppose, where we really can start to learn a lot about them just due to the technology advancing and telescopes advancing in the last 20 years. So for me, it's exciting place to study where there's opportunity to learn a lot about some worlds we've known about for a while, but haven't been able to really explore as much as we would like.
It just kills me that we've only ever flown by these worlds once with the Voyager missions. Like it was so long ago, and I'm really grateful that now we have instruments like JWST to give us a closer look. What was it like to finally see those images of Uranus and Neptune through JWST's eyes?
Oh yeah, that was incredible. I mean, I remember some of my older professors talking about their time, the Voyager days, and the excitement of seeing these planets for the first time. And I don't think anything will ever really catch that same sort of initial excitement of seeing volcanism on Io and the close-up look of Neptune and its clouds and all that for the first time. But I feel like I got a little hint of it, perhaps, of seeing the first spectra from JWST of Uranus and Neptune, because, I mean, they're challenging targets. We've been trying to observe them from, ground-based telescopes for years, and we get, some data, but often it can be quite noisy, and to see sort of the precise, clean data that looks almost like a model in some cases from JWST, given its sort of amazing sensitivity. It really was sort of something I had been waiting years to see. And when it came down and I was in a room with Lee Fletcher and some of my other colleagues, we were looking at it for the first time. And it was exciting. It was really one of those moments I don't think I'll forget.
I mean, really, though, it feels like, depending on how the future plays out, there are a lot more nations that are trying to prioritize potentially missions to Uranus someday. And the results coming out of, studies like the one that you and your team have done, but also from all the data coming out of JWST, I hope, reinforces that incentive for us to go back to these worlds, because there's just so much we don't know.
Oh, yeah, absolutely. I mean, as you say, Voyager was the only time we really got a close look at these planets, and that was 1986. I mean, for Uranus. And there's only so much you can figure out from far away, from 20 times the distance between Earth and the Sun. So it's you need to get close to really learn a lot about these planets, and it's a logical next step in our exploration of the solar system. I'd say we got Jupiter studied pretty well. Saturn, we had the amazingly successful Cassini mission. Now it feels like it's Uranus's turn.
Well, can you tell us a little bit about your journey? I mean, you've gone from Cornell to Michigan to Leicester and now to Chile. How has that shaped your approach to planetary science and international collaboration?
I suppose, it's given me different perspectives on the world, just living in different places. In a way, that's sort of a kind of a perk of the job, to be able to, as a postdoc, have a reliable income for a few years in a new place and meet new people. I worked on some different things. In Michigan, it was more exoplanets than solar systems, so it gave me that sort of perspective on the astrophysics and just planets in general. There's a great diversity of planets out there. Our solar system is just one subset, and in some ways, maybe kind of an odd subset of planets. So to be able to work with different people on different topics over the years has been a great privilege. So yeah, I've enjoyed the process of investigating with different collaborators around the world to some extent. At the same time, yes, of course, it has its I don't know where my home is exactly, and in a sense, I feel a little divided, and it's sort of a nomadic lifestyle, but yeah, is what it is. There's the planets, they're there to kind of, give me focus as I look from different perspectives.
For decades, Uranus has presented this kind of heat mystery. Early Voyager 2 observations, and you said they were in 1986, which is 39 years ago, they suggested that Uranus wasn't emitting this excess heat that we expected from other gas giants. Could you talk a little bit about this long-standing puzzle and why it's perplexed planetary scientists for so many decades?
Yeah, sure. In general, Uranus is a bit of an oddball. As a planet, it's the coldest planet in the solar system, and it's about as cold as any planet we really know of. It gets down to around 50 Kelvin. And so this is colder than the temperatures you see on Neptune, which is farther from the sun. So there's already something a little weird there. Uranus, as I guess we'll talk about in a little more detail, is unlike all the other planets, is tilted on its side. And essentially, Earth's axis is tilted 23.5 degrees or something, so that it gives you these the seasons. Uranus is tilted in something like close to 98 degrees, 97.77 or something like this degrees, and as a result, you get these many of the high latitudes fall into decades and decades of darkness, followed by decades of light. So you get these cold, dark winter nights, which last 30, 40 years near the pole. And then on the other side, you're getting daylight for decades. And so this is sort of extreme setup in terms of sunlight falling on the planet. And even though that sunlight is 19 astronomical units out there in the edge of the solar system. That sunlight is something like 370 times weaker than we get on Earth. It still adds up. It still provides energy to the planet. But what's sort of odd, I guess, about Uranus compared to the other planets, aside from these other facts, is that all the other giant planets, Jupiter, Saturn, and Neptune, if you look at the amount of heat that comes off those planets, the amount of heat that they radiate, it exceeds the amount of heat they actually absorb from the sun. As I say, they're not in equilibrium. The amount of energy falling from the sun enters the atmosphere, that warms the atmosphere. If it was perfectly in equilibrium, the amount of heat it would give off would be equal to that amount. So it's not heating or cooling over time. It's just getting a certain amount of energy from the sun and then radiating that same amount of energy off into space. But it turns out Jupiter, Saturn, and Neptune all radiate excess heat. And so it must come from some internal heat source, some sort of theorized that essentially primordial heat from their formation or their contraction or the way they're still separating, differentiating over time. So they're still sort of evolving. And as they're evolving, they're losing energy still. They're still losing heat and cooling down. And so we have determined this for the planets to occur. But for Uranus, it seems the case is somewhat different. When we did the same sorts of studies, when I say we, scientists back in the Voyager era, did the same sort of studies, they realized that the amount of heat that Uranus gave off really didn't exceed the amount it was receiving from the sun by much, if at all. And so within error bars, it seemed like it was perhaps in equilibrium with the sun. The amount of energy emitted seemed to be about equal to the amount it received, which was very different than the other planets, as we said. And I think the other planets, in the case of Jupiter, something like 1.67 times as much energy is emitted than it receives. Saturn is 1.78. And Neptune, estimates are something like 2.5 times or 2.7 times as much energy is emitted than what it receives. So there's a lot of internal energy coming from its interior that's escaping and being lost to space. But for Uranus, it's something close to 1, where basically it's the amount of energy it receives is equal to the amount of energy it emits. To make these measurements is not easy. You can't do it necessarily from Earth alone, because you need to know how much energy is entering the atmosphere and how much is being scattered back. And from Earth, if you look at Uranus, you're only really seeing the side of Uranus that is facing Earth and the sun. And so you know how much light is being scattered directly back towards you, but you don't know how much light is being scattered in other directions unless you're observing Uranus from those other directions. And so as a result, from Earth, you can only say something about its geometric albedo, as we call it, and you don't really get a full picture as to how much of that sunlight is actually being scattered in other directions. And so to get that measurement, you need to observe the planet from a different range of observing geometries, different phases, as we say. And the only way to do that is to have something like a spacecraft go out and observe it at these different angles, as it's, in the case of Voyager, flying past Uranus. And so what the Voyager mission did was allow us to get these observations of all the giant planets at different phase angles over a range of angles to see how this light from the sun is scattered off into different directions. Basically, just an accounting problem. The amount of energy in versus the amount of energy out.
But what did Voyager actually tell us about how much heat was escaping the planet into space?
Well, you need to be able to look at the thermal emission from the planet from all positions on the planet. And so again, with the same problem, if you're looking at Uranus from Earth, you're only seeing the heat that's escaping from Uranus in the infrared directed towards Earth. And in order to know how much heat's being lost all around the planet, you need to be able to look at what's going on the other side. From Earth, you can't tell how much heat is escaping on the dark, cold night side of Uranus out into space. You just have no idea from looking at Earth alone. And when Uranus being tilted on its side, when it's rotating, you're not getting any of that night side into your field of view over the course of a day. It's blocked from your view for 30, 40 years. So it's really, it's a mystery as to what's going on back there without having a spacecraft kind of go right behind and have a look. And so what Voyager did in flying by gave us those measurements of how the light is scattered as a function of angle going past the planet, but also how much heat was actually escaping from the night side of the planet. And so Voyager, with this infrared spectrometer, was able to measure the thermal emission. I should say, when it flew by in January 1986, I think, so we're coming up on just short of 40 years. It was summer solstice, near summer solstice on Uranus for the hemisphere facing Earth, right? And so you had the half the planet was in winter solstice, and that winter solstice meant that we couldn't really see what's going on there without Voyager. And so Voyager was able to measure the planet at this time of solstice, where one side is summer, one side is winter. And what it found was the temperatures were not all that different between the two hemispheres. Roughly, it was symmetric, where you had sort of warm at the equator and then colder at mid-latitudes. And there was a little difference between the hemispheres, maybe something on the order of just a few Kelvin. But it wasn't dramatic. It wasn't extreme, which is sort of surprising when you think about, you might expect that side that hasn't seen the sun in 30 years is just cooling off, radiating heat, and would be much colder than the day side, which is getting baked by sunlight, weak sunlight out at that distance in the solar system, but still getting irradiated. You might expect a significant difference. But in fact, it really didn't seem to be much of a difference, which has implications. It means that, heat energy is being deposited on one side, not on the other, by the sun. And the fact that they don't differ by that much in temperature means that energy is being redistributed somehow, through winds at some height in the atmosphere to kind of equilibrate and give it sort of an average temperature. But back to the point is that once you know how much how much solar energy is coming into the planet, taking into account that's scattered off in all different angles versus that which is absorbed, you can come up with what's called a bond albedo. And that's what these scientists, guys like Pearl back in the Voyager era, did to determine what the energy balance was of the planets. And when they do that for Jupiter and for Saturn and for Neptune, you find the amount of energy greatly exceeds that which it receives from the sun. So there's an internal source of energy that's quite significant that's contributing to all the energy lost into the space. And that is to say that these planets are losing energy. You can think about maybe in terms of evolution, the planet's still cooling down and contracting, and it's not yet reached its sort of steady state. But when you do the same one for Uranus, they found that, well, unlike the others, it doesn't seem to have much excess energy. It seems that within error bars, basically, from those original Pearl paper back in the 90s, that the amount of energy escaping from Uranus was within error bars consistent with the amount that's being received, statistically significant with it being in equilibrium. And so that was weird because, Neptune, which is a lot of ways similar to Uranus in size, roughly similar size, roughly similar mass, roughly similar composition out there on the edge. It's, its sister ice giant is giving off more than 2.5 times as much energy. So something's weird about Uranus. And people over the years have speculated, well, what's going on? Did we catch Uranus at some strange time in its history where, is there a clue, the fact that Uranus is tilted on its side? Perhaps this all is due to one very violent, dramatic collision early in the history of Uranus that knocked it on its side, but also maybe stirred it up or mixed it in a way or caused it to dispel some of this internal heat that the others are now just sort of slowly radiating away. So it's been a mystery for a while.
How does that impact the level of mixing in the atmosphere?
It contributes to sort of Uranus as being this kind of oddball, strange planet. Without that internal heat escaping, the atmosphere then becomes you don't have that extra source of heat from below. And that's part of the reason Uranus is very cold. And you don't get the same sort of mixing that we see on Neptune. Neptune, if you look at the atmosphere of Neptune, there's a lot more methane up high in the atmosphere because it seems like it's being mixed up higher. It's there, therefore it must be getting mixed up higher. Whereas on Uranus, you don't have that same amount of methane up high, which is consistent with it essentially not being mixed upwards.
But what role does methane actually play in Uranus's energy balance or its photochemistry?
If you don't have that internal heat leading to that mixing, then Uranus ends up being kind of drier up high, and you don't have this as rich photochemistry that occurs when methane interacts with sunlight, produces all these other hydrocarbons. The methane gets photolyzed. You end up with carbons and hydrogen floating around, and they recombine. They form all these different hydrocarbons. like ethane and acetylene and benzene and these sorts of things that were then themselves are very effective at radiating heat, and so they affect the energy budget of the planet too. So it comes to this sort of complicated picture where the interaction between sunlight and chemistry and heating and where gases are and internal mixing all comes together to give you this complicated picture as to how the planet evolves and what sort of a composition and temperatures it has. But Uranus, for whatever reason, this has this different tilt, has this lack of internal heat, and it leads to it being kind of cold and maybe less vigorously mixed, and maybe from an observational point of view, a little more quiescent than the other planets. Neptune, you probably all familiar. You see these pictures of clouds moving along Neptune very quickly. In Uranus, you have some clouds, but you don't have the sort of same dynamic, rapidly changing and frequently seen clouds as you see on Neptune. But and we're starting to unravel this, learn about this. JWST is providing some insight into this, but numerous studies over the last 20 years have really been helping to give us more information on these planets. They're challenging targets because they are far away compared to Jupiter and Saturn. I mean, Neptune is smaller than the Great Red Spot in the sky than Jupiter. So it's a tiny thing, and so you need a big telescope in order to observe it. And really, we only had telescopes that were big enough to observe it well with adaptive optics since maybe 2000, around year 2000, late 1990s, when you start getting these adaptive optics. The data I worked on for my in graduate school for my thesis was data from the Palomar 200-inch, the 5-meter telescope, which is a telescope from the 1940s and 50s, but adaptive optics that allows you to correct for the seeing in the atmosphere was a game changer. It allowed us to really see details on the planet from the ground for the first time. That only occurred in the early 2000s, really. You had data like that. In the 1990s, you had Hubble, and those gave us some nice kind of views of Uranus and Neptune for the first time, that you can see kind of the structure in the atmosphere. But those JWST images show for the first time is if you look at Uranus over time, you start to see there's a very seasonal cycle to it, because it goes around the sun every 80, 84 years, which means that each season is around 20, 21 years long on Uranus.
God, so long.
Yeah, it's a long time, but don't get me started on Neptune. Since that tilt, you get these very extreme seasons again, where you're having 20 years where summer and the pole is basically facing towards the sun, as we were talking about before. But what we found is when you observe Uranus over time, there is sort of a cyclic pattern to its brightness. There's a great set of data. A guy named Lockwood was observing Uranus and Neptune from Flagstaff, from the Lowell Observatory, since the 1950s, I think, and it gave this long period of just annual observations looking at Uranus and Neptune, how they looked each year near their opposition, near where they're highest in the sky. This recorded their brightness. And when you looked at this over time, you found trends where it was cyclic almost, where Uranus would get darker and then brighter, darker and brighter. And it really wasn't clear why this was happening until we really were able to resolve the planet with these bigger telescopes, with Hubble and with then things like Palomar and the big Keck and all these telescopes that came on in the last 20 years that showed that there's a big difference between Uranus's low latitudes and its high latitudes in visible light. You see towards the high latitudes in Uranus, which I mean like latitudes 45 degrees in north or 40 degrees in north, it is brighter, it is more reflective than it is near the low latitudes. For reasons we have come to understand is due to a combination of the high latitudes just seem to have more cloud. There's just clouds around 1.5 to 2 bars that just seem to be thicker at those high latitudes, and they just reflect more light. And secondly, and very interestingly, if you look at the amount of methane in the atmosphere, methane is a sort of dominant absorber in Uranus's atmosphere. If you look at the amount of methane, it varies significantly from the equator to the pole. Near the equator, you have, when you go down to around the bar level, so in terms of atmospheric pressure, you talk about sort of stratosphere up high, these millibar pressures, and then you go down to around a bar, which is basically around the surface pressure on Earth. And then you're in the tropopause, where the weather layer, where things are mixing in the atmosphere in general. And that's where the thickest clouds are, or hazes are on these planets. And Uranus is also where methane becomes more abundant. And this is because on Uranus and the very cold region at the tropopause, where temperatures kind of reach their minimum, the amount of methane just condenses out. You just can't have a lot of it. And so if you look at the amount of methane in the atmosphere of Uranus, it's some small trace amount, 10 to the minus fifth, something like this order of magnitude. But as you go down, it gets warmer, you can have more methane. And then you get down to several percent of the atmosphere by mixing ratio by volume is methane. And near the equator, it seems there was a paper, I guess in the mid 2000s, 2000, maybe 11 or 2009, I forget, from Eric Karkoschka, a great scientist in our field, using some data from Hubble spectra, was able to determine that the amount of methane near the pole differed from the amount of methane near the equator in the tropopause, in the deeper part of the atmosphere. Something like 3 or 4% near the equator and down to 1% or 1.5% near the pole. So a factor of 2 significant difference. And what that means, though, is that since methane's the strongest absorber in this atmosphere, the high latitudes have less methane and quite dramatically, changes quite abruptly at these mid latitudes. And as a result, high latitudes, they're cloudier and there's less absorption, so they appear brighter. And the low latitudes near the equator, they have more methane, they have more of the sunlight's absorbed, and there's less cloud, so they appear darker, less albedo is a term we sort of use, less reflective. And so Uranus has reflective poles and less reflective equator low latitudes. And so when Uranus, since it's tilted on its side, there's points where its poles are facing towards you and points where its equator is more or less facing towards you, and then the other pole and it cycles back and forth over the course of its 84-year orbit. And so that leads to some variation in how bright Uranus appears from Earth. And so what that means is that the amount of sunlight Uranus receives depends on how far Uranus is from the sun, but the amount it absorbs can depend on how much it's reflecting back. And so sometimes in its solstices, it's going to be reflecting more, and near the equinox, it's going to be absorbing more. And so you end up with this change in the amount of heat, that's sunlight that's being absorbed in the planet. Also, turns out Uranus has an eccentric orbit. It's not a perfectly circular orbit. And so as a result, when it's at its closest to the sun, the planet's larger in the sky, it's subtending a larger arc, and it's therefore intercepting more sunlight, and it's absorbing more sunlight. And when Uranus is at its apogee, at the farthest point away of its orbit, then it's receiving less sunlight. It turns out this is quite a dominant factor. This is actually maybe more important than the change in albedo just due to the clouds and methane and the orientation of the planet. But so then the question is, how does the amount of energy that it emits over time vary, over time? So that's what the lead authors Qinyue Wang and Li Ming looked at in this paper, was basically how the energy balance of Uranus, given the amount of sunlight falling on it, the amount of sunlight being absorbed by it, and the amount of heat it's radiating away, how it all balances and how that balance changes over time. And that was sort of the crux of this paper.
Was it the fact that you had so much time to look at this world over the decades that finally allowed us to realize that it wasn't in thermal equilibrium? Like, was it just a matter of getting more data?
Right. I think that's, precisely the case. And I guess also critically is this, in recent years, they've recalibrated. One of the other authors, Daniel Wendker, he went ahead and reanalyzed some of the Voyager data and had found that some of the original estimates for the energy is a function of different phases, how it scattered over different angles, could be improved. And he came up with a better revised number, and that revised number was significant, and that sort of changed things to push in favor that maybe it wasn't quite so close to equilibrium as previously thought. So the question is, now have a better measurement, a better idea of how sunlight falling on Uranus heats it up over time. How much of that energy is absorbed versus how much is scattered as a function of Uranus's orbital period and season. So better accounting, the simple accounting adding up photons absorbed by the atmosphere over time to give us the energy coming in. And so now we know how the input energy from the sun changes in time. How does the output energy from the atmosphere change in time? It turns out that only in the last 20 years, technology from the ground has allowed us to make infrared measurements of Uranus with some accuracy that was just not possible before the early 2000s. And so guys like Glenn Orton over at JPL have been making measurements, infrared measurements of the giant planets using big telescopes to measure the thermal emission in the mid-infrared. Most of the energy emitted from Uranus and Neptune, given their cold temperature, is going to be in the far infrared. But the mid-infrared is more easily accessible from the ground, and we can get a sense of, at least sample how much heat's escaping at some of these wavelengths. And from that, we can relate it to the amount of energy given off in total, just through some careful relationships between that. In this paper, Li Ming and Jinwei have looked at to say how you can relate the brightness temperature, as we call it, these observations of thermal emission from the Earth, to the sort of total amount of energy escaping from the planet. Over the years, we had some observations collaborating with Glenn Orton, Lee Fletcher, myself, did infrared observations of Uranus in the 2000s and again in 2018. And again, in a few months' time, I'll have some new observations from the VLT. These are using telescopes that are 8.5 meters or so, and diameters are large, and they can resolve Uranus, and they're up high in mountains and here in Chile, and they can get some pretty good measurements of the thermal heat escaping Uranus, reaching Earth. And with these measurements, with some extrapolating, using this sort of relationship between brightness temperatures observed from Earth and what we saw, for example, Cassini and Saturn, the authors of this paper were able to infer what the global thermal emission coming from Uranus was over time. And what we'd found, well, there's a couple things found. This in a paper in 2015, and then a paper again in 2020. Glenn Orton and I looked at the thermal emission we sensed from Earth of Uranus, and we compared that to what Voyager gave off. And if we put into, say, the same circumstances, the same geometry, if we're looking at them, say, comparable, it turns out they were pretty much exactly the same. They didn't vary at all, which is to say over 30-something years in a whole season on Uranus, from solstice to spring, the atmosphere didn't really change much in temperature, which is to say it seems to be rather invariant over time, at least onto the measurement uncertainties.
We'll be right back with the rest of my interview with Michael Roman after this short break.
This October, NASA needs you. Hi, I'm Jack Corelli, Director of Government Relations at the Planetary Society. In response to unprecedented proposed budget cuts to NASA's science programs, the Planetary Society and a coalition of our allies and partners are organizing a special day of action to save NASA science. Join us in person on October 5th and 6th in Washington, D.C. You'll receive training on effective advocacy from our team of space policy experts. Then head to the Hill to meet directly with your representatives in Congress to advocate for protecting NASA's science budget and ongoing missions. If you can't come to Washington, D.C., you can still pledge to take action online. We'll give you the resources you need to be part of the movement to save NASA science. This event is open to any U.S. resident, no experience required. Space science benefits all of humanity. Let's stand together to protect it. Registration is open now at planetary.org/day of action. We'll see you in Washington.
Well, that sounds like a little bit of a paradox, right? Uranus has these huge seasonal swings in sunlight, but the temperature hardly budges. What does that tell us about how the atmosphere works?
This implies that the timescales for the atmosphere to respond to changes in the amount of sunlight coming in are really long, and maybe longer than the timescales of a season and the orbital period of Uranus. So that even though you're heating it up one time and then putting it in complete darkness for a while, that doesn't happen for a long enough period of time to actually cause a change on the planet in terms of its temperature. It seems that there's very little, despite the great seasonal variation on Uranus, where you have decades of constant sunlight and decades of constant darkness. It doesn't seem to have much effect on the temperatures, at least at these heights in the atmosphere, at these pressures that are most strongly radiating, emitting their heat to space. So the planet just doesn't seem to have much in terms of seasons, in terms of temperature swings, despite this, our sort of, I say, intuitive, naive expectations that you have this planet when it's going to be pretty extreme, right? You expect it to be freezing and then getting cooked on one side, but it just doesn't seem to be the case. It seems that the amount of sunlight falling on it varies greatly over the course of the year. I mean, complete darkness, complete daylight, a eccentric orbit leading to changes over the course of its orbit of the amount of sunlight it's receiving.
Right. Different albedo even.
Yeah, so the albedo and its relative distance from the sun changing, that's leading to a variable amount of solar energy being deposited into the atmosphere of Uranus. Yet, from the thermal point of view, from the amount of energy escaping, it doesn't seem to be any statistical variation in the amount of energy that actually escapes from the planet. So the amount coming in varies, the amount going out doesn't seem to vary much. And so that implies that energy being deposited from the sun is being redistributed in a way such that you're ending up with a structure that is insensitive to the seasonal swings in sunlight.
That seems really weird when you think about it, because we're saying here essentially like there's not a huge amount of mixing going on because while it's not in thermal equilibrium, it's close. And now it's taking a long time for that heat to go around the world, but in such a way that it's just kind of keeping static between seasons. Like that is so weird.
It is weird. And it's and I guess to this also the point that this new analysis, these new studies with these new measurements, and the things that Pearl weren't available back when this first study came out. The revised quantities of this phase function, revised quantity of albedo, and that has allowed for us to revise this energy balance. And what we found is that with smaller error bars also is that the amount of energy that's emitting is actually in excess of the amount it receives. So whereas Pearl's measurement was maybe slightly in excess, but error bars were indicating that it is still statistically consistent with being perfectly in equilibrium with the amount of energy it receives. This new study says no, actually, when you look at this a little more carefully with this new data, in fact, Uranus is giving off more energy than it receives. So it is closer to more like the other planets in that it has an internal heat flux that is escaping, and the planet is in fact cooling off still over time. And so ends up becoming an interesting thermodynamic problem because it's basically two things. We know there is some source of internal heat that's escaping from the planet. That internal heat we can maybe presume is constant over time, but we don't really know. And the amount of heat that is falling on a planet we know is not constant over time, but it's being distributed very efficiently such that you're not getting these extreme variations in temperature over time, which is all pretty weird. I should also just shout out, there's another paper that came out basically the same time by some of my other co-authors, Pat Irwin leading this one. He did a very similar analysis. In that case, they did some modeling of what the scattering would look like using a theoretical model, a radiative transfer model of given what we know the clouds are like, the hazes are like, and the gases are like in the atmosphere, constrained by observations. Given that, if you take this model, the atmosphere and its gases and its clouds and hazes, and you shine light on it and you look at how it's scattered over time, it gives you sort of a numerical model, a simulation as to how this light scatters over time, as opposed to what we kind of did in this study was to look at observational data and sort of extrapolate. These are kind of different works. But what they found is very, very consistent, pretty much the same thing. They have, it's within error bars, more or less agreeing there is an excess heat flux, internal heat flux from Uranus, contrary to what we for the last 30 years have been saying to be the case based on these original Voyager studies. So it's revised our understanding of the heat flux. It's still really small, and it still needs explanation. And so it doesn't sort of make everything right and place Uranus right in line with the other planets. It's still a weirdo planet that needs some explanation. So it's a privilege to have been involved in this work.
And really wonderful that we now have a long enough timeline on this world that we can try to piece some of this together. But I am wondering, given what we know now about the seasonal variation, is there like an optimal seasonal configuration that you would like to see for us to then actually have an orbiter around Uranus during that time? Because, we could conceivably go back during the same configuration that Voyager had for us and maybe not learn as much.
Yeah. I mean, so Voyager looked at it. It was near solstice. It would be great to look at it near equinox. And to be honest, as far as our options, solstice is coming up. Next solstice is coming up pretty soon on Uranus in 2030. And so we're not going to get a spacecraft there by then. So a good starting point or a good target would be to observe it around equinox. That way we can see both hemispheres in daylight and get a good view of the planet, illuminated at all latitudes, as opposed to not being able to see invisible light, what's going on the night side, for example. So, yeah, I think these sorts of seasonal milestones, the solstices, the equinoxes, are a nice time you can learn a lot about the planet at these periods. And so having a spacecraft that, say, launches sometime in the next 10 years, gets to Uranus near the solstice in near 2050. So we can cross our fingers on something like that.
Yeah, it gives us a good reason to be patient for it, other than just waiting for budgets to clear up, right? But also we're in this interesting phase in our exploration of the universe where we're right on the border of almost 6,000 exoplanets at this point confirmed. We're getting there. We're not there yet, but we're going to be there soon. And so in some ways, I'm really glad that we have this world as an outlier for whatever reason. Maybe it's tilt, maybe who knows what's actually creating this situation, but that gives us another world that we can look at to compare against some of these other potential ice giants in other exoplanetary systems.
Yeah. I mean, a lot has been said when you look at these sort of statistical studies, these population studies of exoplanets. The most common size planet is something in the neighborhood of Uranus and Neptune. It's something close to that, several Earth masses that Uranus and Neptune are basically the closest things in our solar system to the size of the maybe most common size of exoplanet. So to some of us, it makes Uranus and Neptune even more compelling targets because they may be in some way representative of a class of planet that is extremely common across the galaxy. And here they are right in our own backyard. And so Uranus and Neptune have the potential to give us greater insight that could be extrapolated, or greater insight into what may be going on these other planets out there that are, say, hopelessly far away for this type of detailed studies. So yeah, I mean, I'm optimistic. I'm hoping that I'll see a Uranus mission someday, because that'll be it'll be a culmination of a lot of work and something that I just would love to behold.
Well, I know the United States is talking about it because it is one of the priorities in the Planetary Science Decadal Survey. But even if that doesn't pan out, there are some plans from the European Space Agency. There's some plans from the China National Space Administration. So fingers crossed. I believe it. We can hold out. We're going to see this mission sooner or later.
Yeah, humanity will get to Uranus someday. Hopefully sooner than later, and hopefully by equinox at least. Because that'd be great to see. These planets are dynamic. Things are changing. The seasons on Uranus are changing, and we're approaching solstice. I think it's a wonderful time to be studying Uranus and Neptune science. So, which is why I sort of a bit obsessively working at it over the past few years, and I hope to continue in the years ahead. But yeah, it's a privilege. I hope the community agrees, and we and Congress agrees, and we can start gear up towards the next big mission to look and discover things about it that we'll never learn any other way.
Well, for the people who want to learn more, I'll be sharing this paper and all of the other papers mentioned in this conversation on the website for this episode at planetary.org/radio. Thank you so much, Michael.
Take care. Thank you.
See, now I'm doubly convinced that we need a dedicated mission to Uranus. There's so much left to learn. For example, we just discovered a new Uranian moon. Using the James Webb Space Telescope, a team led by Mariame El-Mutamid at the Southwest Research Institute has spotted a previously unknown moon orbiting the ice giant, designated S2025-U1. It's the tiniest and faintest Uranian moon that we've discovered so far. The object was detected in February 2025 in a series of long exposure images from Webb's near-infrared camera. Even Voyager 2, which gave us our first close-up look of Uranus nearly 40 years ago, completely missed it. This brings Uranus's known moon count to 29. We'll talk more about that next in What's Up with our chief scientist, Dr. Bruce Betts. Hey, Bruce.
Hello, Sarah.
Man, this is the first time I've had a true occasion to talk about Uranus on the show, and I cannot wait to see how many jokey emails people send me about it.
I used all my really good random space facts years ago about Uranus, but I got some good ones. It's discovering moons. That's why every time I write about moons in the outer solar system, like in kids' books, like, hey, don't worry about memorizing those numbers too closely, because we keep discovering them, and it's impressive. This is a really far away, tiny object. People discovered using James Webb Space Telescope. Go on, Sarah, tell me more.
Well, I mean, it's really cool watching the way that we're progressing in finding new moons. Like the war between Jupiter and Saturn, who has more moons, I think is really interesting. But because we don't have these dedicated missions out to Uranus and Neptune, there's so much that we don't know. So in the midst of learning more about this world and setting up for this interview, suddenly we get the story dropping that we found a new moon of Uranus, which is all the more reason to love these JWST images.
Oh, they're amazing. I mean, we've had images, but it's the usual. We got a better telescope. It's super cool. We can see things better. You can see the rings. You can see everything better. That's the nutshell.
What do we know about this moon so far?
It is, I think, believed to be about 10 kilometers in diameter. So, compared to a city, pretty good size compared to moons. It's one of the closer ones to the planet that have been discovered. It's in a prograde orbit, so it's going the same direction as the planet is spinning, is in an equatorial plane along with the 5 big moons. Bigger moons, they're small for the solar system, but they're big enough to be round. And then you got little guys like this. So moon number 29, and fits in. Now there are 14 of these small moons hanging out closer in equatorial plane going prograde, and then there are ones farther out that are just wacky, zany, retrograde, and all sorts of craziness. And they usually form in different ways, but it's at least that's the guess. It needs a name, but it gets the official designation S2025-U1, which is actually one of the simpler designations since it's satellite. Year was discovered, U for Uranus, and first one discovered in 2025.
Wow, yeah. I was wondering why that name was so simple. But really, though, I think one of my favorite little random space facts when I was a kid was about the naming of the moons around Uranus, because I was one of those kids that just loved Shakespeare. Not to put aside Alexander Pope, the other author who gets some names around Uranus, but I just love that as a naming mechanic. What would you name this moon? Like, do you have a favorite Shakespeare character you would name it for?
I wouldn't describe it as a favorite Shakespeare character, but I would describe it as one that I would just enjoy people doing science and having to use the word bottom. So at Midsummer Night's Dream, I'd name it after Nick Bottom. Just name it Bottom.
Name it Bottom.
Because it's just funny. Just stupid. What about you?
Well, my favorite Shakespeare play is Much Ado About Nothing. So if I was being serious about it, I would name it Beatrice, because I love that character. But if I was being funny about it, I would go for Dogberry.
Dogberry. That's awesome.
It's a great name and a great character in that play. He is so freaking funny.
Somehow I've never seen that one or read that one. All my teachers, we always had to read the tragedies. It was a real bummer.
Oh, man. Highly recommend Much Ado About Nothing if you love shenanigans falling out from totally silly reasons.
Shenanigans are one of my favorite things.
You would love Dogberry.
Dogberry. I changed my vote. I want to go with Dogberry.
We're submitting it to the IAU right now.
Yeah, and I'm sure they'll discover more. Poor Neptune. Maybe we can start cranking up the Neptune numbers. Saturn's just gotten ridiculous. I mean, Saturn's just it decided to just leap forward in the standings. Yeah, I think it has about 1 billion. Oh wait, that's only if you count the ring particles. No, never mind.
I was going to say, but the moons of Saturn are really interesting, I think, for me, in that some of them are being created from the ring around it. So in my brain, something smashed up, some moons or something, created this ring around Saturn, and now it's reforming cute little potato-esque chaos demons inside of the rings.
Chaos demon. Oh, and don't forget the ravioli moon. Anyway, yeah. We like moons. We like moons.
So, what is our random space fact this week?
Space fact. So, speaking of traveling, desperate attempt at a segue. So I was curious, going out to Neptune, being way out there. I mean, it's 30 AU, with AU being astronomical unit, average Earth Sun distance, but you don't go straight to any of those places. So I was wondering, how far did Voyager 2 go to get there? And it went about over 7 billion kilometers, but it got there in a wonderful 12 years, which is one indication of just how very far this is. But what's really interesting to me is that by using the gravity assist of doing the grand tour, Jupiter, Saturn, Uranus gravity assist, it cut, at the time, for what the estimate was, at least with that configuration, 20 years off. It still took 12 years. Without the gravity assist, it would have taken 32, I guess. At least that's the NASA reports.
That's crazy. Okay, so I'm in Uranus brain. So it flew by Uranus in 1986.
86, yeah.
When did it go by Neptune? 89.
89.
So if it had taken 20 more years, whoa, I would have been... well, alive for one, but also no. That's just crazy. 2000s. Whoa.
I mean, you probably wouldn't have launched it, frankly, if you didn't have. And you can do faster with bigger rockets and with smaller spacecraft, and so the New Horizons was sent out of the Earth Moon system going faster than anything else had been at that time anyway, although it's been slowed down by the pesky sun's gravity. So they flew a small spacecraft, and they got it out. They went to Pluto in 9 years or so. So
yeah.
They're booking it.
Yeah.
To use a technical term.
Technically, but no, really. I mean, it's just a great example of the advancement of our technology over time. And yeah, here we are. We haven't sent one out there yet in a long time, but we can look at it with JWST, this crazy telescope, and learn more, like the fact that there are new moons out there that we just didn't know existed.
Yes, they're new to us, but not to Neptune.
Yeah, they've been out there for a long time.
Uranus, sorry. Whatever. I'm sure there got to be more hanging out at Neptune. Voyager picked up, 14, I think. And so we're looking for more. Let's do it. We'll go out. We'll get. We can get like 3 or 4 inch telescope. I'm sure we'll do it. We can hallucinate. All right, everybody, go out there, look up the night sky, and think about how long you would take to go to the grocery store if it were on Neptune. Thank you and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week to give you a peek at the upcoming International Observe the Moon Night festivities. We'll let you know how you can join in no matter where you live or how the weather shakes out in early October. And speaking of celebrating, next week I'm going to be flying off to Philadelphia, Pennsylvania in the United States to host the webcast for NASA's Innovative Advanced Concept Symposium. This is going to be my third year doing it, and I'm really looking forward to it. So if you want to watch the webcast, I'm also going to provide a link for that on this webpage at planetary.org/radio. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can send us your space thoughts, questions, and poetry at our email, planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members who love a good planetary mystery. You can join us as we advocate for future missions to the ice giants at planetary.org/join. Mark Halverda and Ray Paoletta are our associate producers. Casey Dreyer is the host of our monthly Space Policy Edition, and Matt Kaplan hosts our monthly Book Club Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. My name is Sarah Al-Ahmed, the host and producer of Planetary Radio. And until next week, Ad Astra.